Hello everyone and welcome to this lecture. Let us have a quick recap of what we have done in last 3-4 lectures. Okay, so we have discussed about expanders. So these are the graphs which were sparse and well connected. So we were focused on d regular graph because for a fixed degree when you are increasing n, the edges actually grow linearly. So these are the sparse graph for us, but they were well connected. The expanders graph were well connected. Then we gave some results, some interesting theorems on expander graphs, in particular expander mixing lemma. Okay, and then we talked about the optimal expanders, the expanders which are the best possible. Okay, and these we call as Ramanujan graphs. So they were following which property? If the second largest eigenvalue is less or equal to 2 into square root of d minus 1, where d is the actually the number which is basically d regular graph we are talking about. Okay, so such graphs are called Ramanujan graphs. Okay, and now in this lecture we will see a try to construct or give some existence of expanders or Ramanujan graphs. Remember, we have seen that coming up with the explicit construction of Ramanujan graphs or expanders is extremely challenging task, even though due to Friedman, every random deregular graph tends to be Ramanujan graphs for sufficiently large, and but explicit construction is very challenging task. Okay, very good. So let us go ahead with this lecture. We will be talking about two very interesting things. One is about two lift of graphs, okay, and another thing is about zigzag product of graphs. Okay, very good. So let us go ahead with two lift of graphs. Okay, so I will giving you first a picture of it, and then we will tell what formally tell what two lifts are. Okay, so basically so let me move to one more slide. Okay, so two lift of a graph. Let us see about what is two lift of this graph. Okay, what is a two lift of graph? Okay, the first thing is place two copies of this graph. Suppose this graph is G, so I have placed two copies, so G and G, maybe you can call G1 and G2. This is essentially the same thing. Okay, now to each edge of this graph, either you keep this edge as it is in both the graphs or cross it. Okay, so for example, if you see this edge 1 4, it is as it is in both the copies, in this G also, in this G also. Okay, but and similarly I think about okay, and let us focus on here, this graph. Okay, so now let us see what happens for 1 3. Okay, if you see that 1 3 is actually getting crossed. Okay, so 1 3 is actually the one of this first copy is having edge with 3 of the other copy, and vice versa. Basically this 1 is now have edge with 3, but this 3 is of another copy. Okay, then you see that similarly edge, I think this 2 3, if you talk about this as 2 3, this is also crossed. So second vertex of the first graph is connected to the third vertex of the second copy of the original graph. Okay, so this is also crossed. Rest of the edges are not crossed. Okay, so for example 4 3, this 4 3, here it is as it is, and here also as it is. So this is a two lift. Basically you pick any edge, either you keep in the keep this as same in both the copies or cross it. Okay, and all these are what these are called two lifts. There are various kinds of two lifts. In fact, this is also two lift, this part where none of the edges are crossing. Okay, okay, so you can give many what we call this two lifts of graph. Okay, so in this particular case, in this, if you see that this is a two lift. Okay, so these are two lifts. Yeah, and here edge 1 3 and 2 3 of the original graphs are crossed. Okay, by the way, how many vertices are there? There are 2 n vertices, where n vertices are in original graph, then there are 2 n vertices in your two lift. Okay, now let us take some more examples. Okay, okay, so this cube, we have seen already this cube many times now. So this is nothing but Q3. Okay, hypercube graph Q3. Okay, this is a two lift of K4. Okay, maybe you can easily see that you can actually cross these two edges. Okay, you take two copies of this same graph and then cross these two, and it will give you it will give you Q3. And similarly, this graph is a two lift of this. So some edges you pick and cross them. Okay, very very simple. I hope you got the basic idea what two lifts are. So maybe I can actually give you slightly more formal definition but I hope by the now you actually know what we mean by two lift. So every edge in the original graph, okay, so either you keep edges in both the copies, okay, or you cross them. Okay, so resulting graph will be R2 lift. Okay, now what is interesting about this? Okay, the interesting thing about two lifts are actually its eigenvalues. Okay, by the way, so there will be how many vertices? There will be 2n vertices. 2n vertices. So this is suppose there are n vertices. Yes, how many? There are 4. So there will be 8 vertices. Okay, 2n vertices. What about the eigenvalues? What about the eigenvalues? Okay, the interesting thing is the eigenvalues of this graphs are the out of these two n eigenvalues, half of the eigenvalues are nothing but the older eigenvalues, the eigenvalues of the original graph. Okay, so if you see the original graph is this, its eigenvalues are this. Okay, so these eigenvalues will also be the eigenvalues of this, and there will be other n eigenvalues. What will be those n eigenvalues? Okay, so basically it inherits its old n eigenvalues and it also have some n new eigenvalues. So we are trying to find what will be those new eigenvalues. Okay, the new eigenvalues are actually given by something called signed adjacency matrix, and which is very very easy to define. Okay, this signed adjacency matrix is nothing but adjacency matrix where there are at some places -1 instead of 1s. Where are those -1s? Okay, these -1s are those places where the crossing has actually happened. So for example, you know that crossing for this graph is happened at edge 1 3 and I think 2 3. Okay, so at that place you put -1 1 3. Similarly 2 3. Okay, this matrix is also symmetric. Okay, so you just place these -1. So this is again a symmetric matrix. Okay, and the only difference is whenever there is a crossing, okay, instead of 1 you put -1. Okay, now the beautiful and interesting thing is this: the rest of the n eigenvalues are the eigenvalues of the signed adjacency matrix. Okay, why this happens? So basically, out of two n eigenvalues, the n eigenvalues are the older ones, and the new n eigenvalues are the eigenvalues of the signed adjacency matrix, which is actually given by the crossing. So whenever there is crossing, you put -1. Okay, why this is true? And this actually includes multiplicity. Okay, so this includes multiplicity. So the theorem is that the spectrum of any two lift is actually union of spectrum of your original graph, okay, and the spectrum of the side adjacency matrix, and taken with multiplicities. Okay, very good. So for example here, okay, so these will be the eigenvalues. Remember -1 is repeating here, so we have to actually keep both. Very good. Okay, now what? Okay, now what? Proof. Okay, so why this proof is actually very crisp. Okay, very simple one. Okay, but in order to understand the proof, let us first understand the structure of the adjacency matrix of two lift. Okay, remember in two lift, what will suppose this was the graph. Okay, so maybe actually write down here. I hope this was the graph. Okay, so we have put actually two copies of this. So I think so maybe this was the case. These edges were as it is, and then I think there was crossing, right? So maybe I think let me actually go back. Then I will. Yeah. So 1 2 3 4 I am doing this, and then 1 3 and 2 3 we are crossing. Okay. So 1 2 3 4. Okay. So 1 2 3 4. This was my graph, and this is suppose a two lift where 1 2. Let me again write through that. I do not confuse later on. So 3 4. So 1 and 3 are actually crossings here. So this 3 and 1. Similarly 2 3 is also crossing here. 2 3 is also crossing, and 3 2. Okay. Let me again check. Maybe I am not making any mistake. Very good. 2 3 and 3 2. 2 3 and 3 2. Very good. So now if you see that, what will be the adjacency matrix? So let's suppose denoted by this A hat. Okay. Adjacency matrix actually look like this. A1 A2, A2, A1. Remember, this A1 is nothing but the induced submatrix, or maybe called, suppose this, if you take this part, right, if you take this part, this is A1, induced subgraph on these four vertices. This is same as here, this is same as here, right? So that's why we have put on both of the place A1, okay, induced subgraph on these vertices, right here and 7. And what about A2? A2 is actually signifying this matrix, right? The entries in A2 is signifying by this matrix, right? Remember, this is the adjacency matrix. A star is adjacency, A hat is the adjacency matrix. Sorry. Okay. Now this is A2 here, but the same goes from here to here, right? So I can keep A2 same here. Okay. So this is the structure of matrix here. Now the interesting thing is, using A1, A2, A3. Again, sorry, there are only two. You can actually write down what A will be. A is nothing but the adjacency matrix of this. Okay. A is adjacency matrix of this. What will be A? A is nothing but, if you see that, A1 plus A2. Why? A1 is actually this one, right? The adjacency matrix of this graph, basically induced subgraph, adjacency matrix of induced subgraph. But there are few edges missing here, which were here 1, 3, and 2, 3. You can actually, by adding A2, you can actually put those edges back, and so this will give you the adjacency matrix of the original graph. What about the signed adjacency matrix? Signed adjacency matrix is what? Wherever there was crossing, you are putting -1. Otherwise, it is 1. Right? Otherwise, so this is nothing but this A1 minus A2. Remember, A1 is what? This I said that if you subtract A2 from here, okay, whenever there is a crossing, whenever there is, it will put -1, okay, and A1 is, A1 is giving those ones, right, corresponding to the adjacency matrix, okay, and whenever the crossings were there, you are putting -1 there, okay, very good. So this will be the setup for us. Now, how to prove that the eigenvalues of A hat are nothing but the union of eigenvalues of what? A and AS. How to prove? Okay. Now the proof is in front of you. Very, very simple. So suppose the alpha is eigenvalue of A with respect to and the corresponding eigenvector is, suppose this is the case. Okay. V, and similarly for AS, suppose U is an eigenvector corresponding to the eigenvalue beta. Okay, now just multiply this vector. So this vector VV, okay, suppose this V and V, you will be getting that this is nothing but an eigenvector of A hat for the eigenvalue alpha. Similarly, this is an eigenvector of A hat for the eigenvalue beta. Okay, so this is just just do the matrix multiplication with this vector, these two vectors. You will be immediately get a very, very simple one. Now, is it all? Is it all the determine that the alpha and beta are all the eigenvalue? They are encompassing all the eigenvalue. No, we have to prove that these two actually are the orthogonal eigenvector. We have to prove that these two are the orthogonal. But why they are orthogonal vectors? Okay. Why they are orthogonal? If you take the dot product of them, it is coming out to be 0. Okay, so remember the spectral theorem. Okay, and by the spectral theorem, actually now you see that they actually capture all the eigen. So there will be two n eigenvalues which were actually given by the eigenvectors of the matrices A and A dash AAS, sorry, and the corresponding eigenvalues will be the eigenvalues of A hat. Okay, so very, very, very simple proof. Okay, great. Now there is an interesting consequence of this beautiful concept of two left. Okay, it was conjectured by Billu and Lineal that therefore every d-regular graph, remember we are dealing with d-regular graph here, has a signing, basically a crossing. Okay, crossing we can say, in which all of the new eigenvalues, okay, there will be n new eigenvalues, have the absolute value at most this. Okay, why this is so much significant? This is why this is so much significant. Remember, we have seen that the Ramanujan graph, the best possible expanders, have the second largest eigenvalue in terms of mod is always satisfy this, right? Square root of, so it is always less or equal to 2 times square root of d minus 1. Suppose you start with a Ramanujan graph or a very, very, very well expander. Okay, if there exists a two lift, such that basically if in that two lift there exists some signing, okay, such that new eigenvalues are also following this, then the resulting two lift is nothing but again Ramanujan graph. Okay, a very good expander. Okay, so actually this conjecture is very powerful to give good expanders or Ramanujan graphs. Okay, and in fact this is more generalized statement that every degenerate graph there is an AS or signing with spectral radius. Spectral radius is nothing but the largest modulus, right? Largest modulus of the eigenvalues is actually order of square root of d log to the power 3 by 2 into d. Okay, very good. And very recently, we have seen that Nikhil Srivastav, Marcus and Spillman proved this conjecture for D regular bipartite graph. For every D regular bipartite graph, there exists such a signing, such a crossing, or such a matrix AS. Okay, so they have proven this conjecture for the bipartite case, and by doing so, they have actually given an infinite sequence of D regular bipartite Ramanujan graphs. Okay, very powerful result again. Okay, and in fact later on they have actually proved that this statement holds for every degree and every number of vertices. Okay, so there exist bipartite Ramanujan graphs of every degree and every number of vertices. Okay, and very soon after that actually Michael B. Cohen actually shown how to construct these graphs in a polynomial time. Okay, so very interesting thing is going on. Okay, but this conjecture is still open for the non-bipartite case. So are there exist infinitely many D-regular non-bipartite Ramanujan graphs? This statement, this conjecture is still open. Okay, very good. Okay, now let us move to one of the most interesting product of graph products that we call Zig-zag product. Okay, it was given by these three mathematicians in 2002. Okay, so what is this Zig-zag product? Why this beautiful name or exciting name Zig-zag? Okay, so Zig-zag product is on two graphs. Okay, but there is some constraint on these two graphs. Firstly, both of these two graphs are regular graphs with different regularity. So suppose this is my graph G, where there are n number of vertices. Okay, and suppose the degree is degree of each vertex is m. Okay, now this H will be a graph on the m number of vertices and some degree d. Okay, so this is actually degrees. Okay, degree, this is degree. Okay, this is degree. Okay, and these are vertices, number of vertices. Okay, so you see that the degree of G is nothing but the number of vertices in H. Okay, now you see that just first let us look at the picture, and then I will actually formally define what we mean by zigzag product. You see that in G, okay, so you just look at now this picture. In G, every vertex is kind of replaced by a copy of H. So for example, suppose this was V1, V2, V3 here. So you are replacing every vertex by this copy. Okay, and then how the edges. For the timing, just forget this dark edges. For the timing, forget dark edges. Forget dark edges. Edge of dark edges. Edge of now. Edge of now. Okay. Okay, what we are doing first? Okay, first we are doing this. So we are replacing every vertex with a copy of H. Okay, and then you see that inside, so we call such a configuration, once we are replacing every vertex with H. Okay, that particular H for that vertex we will call as a cloud of that vertex. So for example here, suppose this is your V. Okay, now this will be a cloud for V. So this is a cloud for V. Cloud is nothing but a copy of H. Okay, and all the edges inside the cloud here are actually by the edges which were in H. Okay, so we are not changing those. Okay, now what about the other edges? Remember, I told you just forget about the dark edges. We are only focusing on the dotted edges as of now. Okay, now you see that the degree of every vertex here is equals to the number of vertices in S. Okay, so how the other edges are placed, how these edges and these edges are placed. Okay, so let us see pictorially. Okay, suppose this V vertex and U vertex are from G. Okay, and each of these has the basically the same degree. Suppose in case of here this is 4. Okay, so what you do, this is degree 4, again the degree is 4, and maybe they both have this edge in common. So suppose this is the edge. Okay, now what you do, you order the adjacent vertices of each of these vertices. So suppose the ordering is 1, 2, 3 and 4. So these are the ordering of neighbors of V. Similarly, there will be ordering of neighbors of V. So suppose I call it, so this is 1 now. So this vertex for U will be now suppose 1, 2 and 3 and 4. Similarly, so you see that for V is the first adjacent neighbor of U, okay, but U is the third adjacent neighbor of V. Okay, so in this way actually you can now write this as, so you actually now after replacement what will happen, so there will be a copy of this, right, copy of H here, copy of H will be here, H will be here, whatever the vertex, because degree here is same as the number of vertices in H. Okay, you can now actually give, after placing the H, you can now actually give name as this. Suppose if I place here this guy here, so suppose if here you are replacing this, so this will be now this nothing but, suppose this is V1, V2, V3 and V4. Similarly here it will be what, this guy will be U1, U2, U3 and U4. Suppose if these are two, so this was U, this was V, which was replaced by the H. Okay, now what, how the edges are coming. Okay, now edges are very very obvious here. So you see that these two edges were earlier they were had adjacent edge, right? Now what you do, there will be an adjacent vertex, adjacent edge, basically an edge which will be adjacent on this V3 and U1. It is actually coming from this edge. Okay, now the graph coming from this process is known as replacement product. Because we are replacing every vertex with the smaller graph, having the same number of vertices at the degree of the original graph and the edges given by this. So let us actually formally define what we mean by replacement product. So it is actually the same. So the graph is on n vertex, G is on n vertex, having degree m, and H is having m vertices and degree d. Okay, replace each vertex of G by the copy of H. Okay, very good. Now you can call this H edge a cloud of V. Okay, and inside H now there will be vertices. Okay, inside H now this will be, so Vj is the jth vertex of H inside the cloud of V. Very good. Now edges are edges. So first see the edges which were actually present in your cloud in EH actually. H is a cloud, right? So all the edges we will be placing, all the edges we will be actually keeping as it is. Okay, so this, if Ij was the edge in EH, okay, then there will be this edge Vi and Vj. Okay, very good. Now the next thing is, what about the other edges? Other edges is also very simple. Suppose V is the ith vertex, ith neighbor of U, and U is actually jth neighbor of U in the original graph. Then this edge will be there, right? So Ui and Vj, we have just seen this Ui and Vj, so you will have an edge between them. Very good. Now this was about replacement, but by the way, the resulting graph after a replacement product, what will be its degree? Okay, again this will be a regular graph, but now the degree will be, degree of each vertex will be d plus 1. Why it is so? This is actually very easy to see. Remember, we are replacing every vertex with basically a copy of H, right? So all the edges which were inside the H, we are actually preserving it. So the degree of vertex will be at least this much, but then we have an edge with other cloud also, right? For example here, so this was degree, and we have one edge with other cloud of basically the vertex which was adjacent to the cloud, basically V of the original graph. Okay, so there will be one more incident edge, and hence there will be degree d plus 1. Very good, very simply. Now comes the zigzag product. The exciting one, and now it is very easy to define what we mean by zigzag product. But for this to show, now let me put back those darker edges. So let me erase all this content. Okay, here. Now let us put those dark edges back. Okay. What is the rule to put these dark edges? If you see there is a dark edge, so let me call this is vertex V, this is vertex V. Okay, we have put this dark edge due to the following rule. Okay, so what you do, you see that from V you can go one edge there, then so one edge inside this cloud, so this is cloud, this is a cloud, okay, then an edge between the cloud, then this is another cloud, okay, and then we are reaching here, okay. So this is a kind of pattern where, suppose this is a cloud here, you are edging, basically putting one edge here, okay, then between the cloud, then another, suppose this is a cloud, okay. So this is zigzag jig, okay. Whenever such possibility is there, you put the dark edge between these two vertices, okay. Now in your in the resulting graph, only the darker edge will be there, okay. Okay, just forget about the dash edges. The resulting graph will be known as the zigzag product of G and H. G and H, okay. So I mean, let us see again the another dark edge, the same thing, right? So suppose this one, why this dark edge is there? Because you can go here inside the cloud, then between the cloud, then inside the cloud, okay. Very good. It's a kind of path on 4 vertices, okay. So one edge inside the cloud, one edge is between the cloud, and another, the remaining edge is again inside the cloud, okay. So there is jig, jag, jig, okay. So these edges will be, then you have an edge basically between you and, so let me call it W, okay. In this way, for every pair of vertices in this replacement product, every pair of vertices, if thus such is the possibility, you put an edge between these two vertices, okay. By the way, what will be the degree of each vertex in this case? The degree will be equals to d square. Remember, the d is the degree of h, okay. What will be the degree, okay? Why the degree will be d square? Why the degree will be d square? Okay. Now remember, the first condition is that we have to move inside the cloud, okay. So suppose you pick any vertex here, okay. For the inside the cloud, how many possibilities are there? There are d possibilities, right? There are d possibilities because the degree of h is d, okay. So here it is 2, okay. And then what? You have to go to enter, basically you have to pick one edge, and there is actually one edge, okay. So once you select this vertex, okay, so you have to go here, okay. Now again you have d choices to reach to some other vertex. So that's why it's a d into d square. So the resulting graph will have will have each vertex degree is equals to d square, okay. And the number of vertices are same. So replacement product, after replacement product, zigzag product is very simple to define, okay. So vertex size is the same as the vertex side of your replacement product, okay. And now this will be the edges, okay. So these will be the edges. This actually says that if the vertex, this vertex Vj can be reached from the vertex Ui by taking a step in the cloud of U, then taking a step between the clouds of U and V, and finally a step inside V, okay. So this is actually the formal way of writing it, okay. Very good, and hence the name zigzag is coming into picture, okay. Very good. Now why we are studying this zigzag product, okay. Seemingly on first glance it looks slightly tricky, but it's very easy to define, okay. We are studying this zigzag product due to its beautiful property with respect to the second largest eigenvalues of in terms of modulus other than the largest eigenvalue, right? Okay, very good. Now suppose n, d and lambda is the graph, it's a d-regular graph, okay, on n vertices with this quantity. We have already seen it many times. So lambda is the maximum of all the absolute values, okay, other than d, okay. And suppose g is this graph on n vertices having m degree and lambda 1 be that parameter, and h is the graph on m number of vertices. Now degree is d, so remember these two are the same here. Then the replacement product of g with h is this. There are n into m vertices, very easy. D square degree, we have seen that, and this will be the eigenvalues. The eigenvalue is this, okay. The eigenvalue always satisfy basically the second, the largest eigenvalue in terms of modulus other than the maximum one, which is equal to degree d square here, will always follow this. That means what? This means that if lambda 2 and lambda 1 are actually small, this quantity will be small. In particular, if you see that suppose h is a very good expander, okay, very good expander means h, this lambda 2 is very small, right? In that case, this guy will be also small. The resulting eigenvalue will also be smaller, right? So basically it says that if you have a very good expanders, then taking zigzag product might give you a again good expanders, at least not worse than, at least maybe not more worse than, we can say, than the original expanders. Okay, so with this I am stopping this lecture. So, and the proof are slightly, I mean, advanced, so I am actually not doing the proof here, so maybe we'll do in some other course. Okay, so very good. So I hope you got some introduction about zigzag product and these two lifts. Okay, so thank you very much and see you in the next lecture.